foundations of physics, or what are the basic ideas, what are the basic ideologies on which the subject of physics stands by itself. Okay. And how these ideas had evolved. Like, it's all of us know that no subject has come overnight, right? So even physics has a journey. It has a journey of so many years, I would say even a couple of centuries. There are n number of scientists and laureates and people and unrecognized people who have given their life for the subject, and yet we don't understand how valuable those things are, how valuable their ideas are, and how valuable they were. So today we'll have a slide, just an introduction to what these areas were and what these areas are. How did the subject evolve to what it is standing currently today? And where are we right now? And what are we going to do later? What can we do later? So this will be today's topics agenda. So as I said, I will not be stressing on any one particular topic as such. In that, of course, you can ask me questions from any topic that you wish to, but my focus will be on a very general perspective, on a very general move on all the essential topics of physics, which I think any student who is in science, who is in physics, should have some clearance about. So that is all about today's topic. So Anna, shall I start with it, or does
Yes,
anyone else want to ask anything from just
uh,
about the introduction or something?
Samir, you can proceed, and then we can see as and when they have questions, they will raise their hands. I'll unmute them, and they will ask questions to you directly.
Okay,
Yeah,
okay,
you can
okay.
start, Samir. And yes,
So let us just have the beginning. So yeah, I mean the first slide is just an introduction. I mean it's about the journey about it. So let's all revert back to the initial times. Okay. So what do I mean by initial times? I mean to the, I know, around the 14th century, 15th century time, just a bit before Newton. Okay. So that is where we are going to start. Of course, that is not the formal starting, but let's not go back so much. So this is where we are going to start. Is it working? Okay. So what is and why? What is physics and why physics? So I think you can see this answer right there. So what is physics? It is a study of stuff around us. It's just a study, it's not some great rocket science or some not very hard topics. It is just some kind of a study. It's some kind of an observation. It's some kind of a deduction, some kind of an understanding of what? It is something of what's around us. Okay, it's something that's right next to you, the room where you're sitting, the AC that's working, the fan that's running, the light that's on. Okay, how, why, when, where. That's basically physics. Okay, that is what the subject deals with. And why physics? Simple, to know about them. There's nothing great about, I mean, if anyone asks you why do you eat food, it's basically because we like eating, right? Or we are hungry about it. Why do we do physics? Because, okay, because we want to know stuff, we want to know what's going around us. Okay, and of course we have a thirst to know about it, so that's important. It's not just about going about something. You really want to know something about it, and hence you choose the subject of physics. So what does it deal with? Let's see that. How is it different from the other parts? You have physics, you have chemistry, you have agriculture, you have literature, right? You have so many things. You have commerce, you have archaeology, you have geography, you have so many things in and around you. How is this subject different? So I have given one answer. Okay, and right here I would like to ask someone if anyone is interested to give any other answer. I think you can see my answer on the screen, right? According to me, it deals with a very fundamental level of matter. We will come to what's the meaning of fundamental level and all. That is something we'll take over. But does anyone have any other answer over here?
so the question is, how is physics different from other subjects? So that is the question. So you can type in your answers if you have any to these questions. It's more fun. I'll read out the answers as they type
Yeah,
in.
that will be helpful.
Yes, I am still waiting for more responses. Adit says it's more fun. I mean, that's you're one of those very few people who says it's more fun, but it's I like
That's
it because
pretty
it's
rare.
fun.
That's
It's
pretty rare.
fun for me as well. Nevertheless, so Cyrus says it's the base for other science. Jayveer says it describes matter. Devya says it's more interesting. So there are two people who says it's very interesting. Okay.
Okay, so two
Okay.
one twenty is a good
Jaiveer
number.
says it is deep and interesting and unlimited learning one can have in physics. I mean, very interesting responses. So yeah, infinite areas to explore. And another person, Shivain, says physics helps us understand how the universe works. So uh, Ram Ramswamy Seduraman says understanding how matter works in the universe. Ashwin says used in our life, most interesting part to learn. Okay, I mean I'm happy with the responses.
I'm really shocked, and as well as I'm really interested, I mean, I'm very happy to see how the way they are saying it out, right? I mean,
And
interesting. Yeah.
Yuvan says it is fun and can tell us a lot of things. So I think we understand your
Yes.
responses.
Definitely.
In general, it is interesting, it is fun, it tells about how the universe works and a lot of other things. I think that's the crux of what
Yes. Yeah.
you were all saying. Thank you, guys. And Samiran, over to you. You can continue.
Yep. So yeah, I mean, all of you are right. None of you are wrong. Everyone is right in their perspective, and that's essentially what physics is. I mean, I am very happy to see that you people are taking physics as a fun subject and not as a hard subject, which generally people take it as. So okay, let's go ahead. So we will deal with something called as a fundamental principle of nature. Okay, see, everything around has works on some principle, right? And physics is nothing but a way to understand the nature. That's all physics is about. That's all everything is about. Physics is just one of those millions of approaches, right? And we choose that approach because we like that approach. There's nothing great about it. So even physics tries to understand the nature using some principles of it. The most vital, the most basic principle is called the cause and effect principle. I think all of you would have heard this some way or the other, somewhere or the other place. So it's called as a cause and effect. So it's basically it's very simple to state, but it's not that simple to understand. We will see why is it not that simple to understand. It's very easy to state in the sense that we can say that yeah, everything that has a cause will have an effect. It's simple as that. So suppose you go and you eat your food, your hunger dies off. So that's the cause was your hunger. You ate the food, your hunger has died. That's it. That's a cause and effect. So anything that happens in and around you will have a cause and will have an effect. So that's a very understandable principle. But what makes it difficult? Okay, what makes that difficult is what we are going to deal in the coming slides. So I have given you a relationship here. If you can look on the screen, it's cause, effect, abstractness, and reality. That looks a little scary, abstractness and what is all these things. It's nothing. It's just some fancy words. Okay, so abstractness means something that you think about, that you are not sure if it actually exists or not. You just think about it. You be like, okay, it might be, it might not be, it might not be this way, it might be in some other way. It's something that you're thinking about. Okay, you don't have any guarantee, you don't have a direct way to say that yes, this thing is real. And reality is, of course, we know what is reality. You are existing, that's a reality. But you are existing is not an abstractness, that's a reality. Okay, I have given a statement here, the reality that we see and all these things. Don't be scared of all that. If you want, you can read them. I'm anyway just telling you what the gist of the slides are. So we will ponder more on this abstractness, reality, cause and effect in the coming couple of slides. Okay. So yes. So let's begin here. So come on. This is the task. You can see that the thing that's on the screen, and there are like four pillars. That is your red, green, yellow, and blue. Right. Our task is to determine what these four things are. Okay, it's about to explore the question marks. So this let us begin our task today. So yeah, as I told you, we'll go back a bit before Newton, and we start from Aristotle, Galileo. I think none of these names are new to anybody over here. So they are known as the pioneers of astronomy. That is, they are the people who actually started, or I don't know if they really started. I have not read so much about them, but definitely I know one thing is that they were one of the greatest people in this branch. One of the branches in which they were greater was astronomy. They were in philosophy, they were in astrology, they were in mathematics. They were. I think there were hardly any field in which they were not great when they were alive. So, and they are the main reasons, because of whom or because of whom findings, the writings of them, we are able to advance in our today's astronomy and our today's physics, and including a lot of sciences, including philosophy. It's only because of what they had written, what they had found, and on what they had spent their lives on. So we'll start from there. We'll not go so much deep into them. I'll just mention a couple of things that Galileo had done. So Galileo has been named or has been respected by the name of the father of modern science. I think you know this. He is known as the father of modern science simply because of the following 4 to 5 things. And again, telling you these are just 4 to 5 things that I've listed. You can actually go on Wikipedia and check out the list of things that he had done. So law of falling bodies. Okay. So he was the first one to say, I think all of you are very familiar with the YouTube video that you drop a feather and a ball, and in your normal day experience you believe that the ball will fall faster. I mean, that happens, the ball falls quicker than the feather. But you go to a vacuum area, you go to a place where there's no air resistance, and you find that both of them exactly take the same time to go come and hit the ground. So that was something that Galileo had first stated. Okay, this is even before Newton. Just imagine. So that is nothing but the law of falling bodies. Heliocentric model, all of us are aware with the name of heliocentric model. He was the first one to say, or at least to claim, that the Earth is not the center of the universe and something like that, which was the most common notion before him and even before Aristotle. So these people were the ones who actually said that no, Earth is not the center of the universe or something, but we are in fact revolving around a sun and all those things. And they were the first people to actually, trace out the trajectory to a large extent, that what is the trajectory does the Earth follow and everything. So that was the heliocentric model. The concept of inertia, I think all of us know the Newton's laws of motion. We will be anyway doing that in the coming 2 to 3 slides. We'll be just looking at them. But the whole foundation of Newton's laws of motion was from the concept of inertia, which was given by Galileo. Okay, of course Galileo did not do it down mathematically what Newton did, and that's the reason we celebrate Newton. But the concept was initially originated from Galileo. That was the concept of inertia. Geometry, definitely a large part of geometry has been contributed by Euclid as well as Galileo. I mean, the planetary motions and everything was actually laid down by Galileo in the very first place, and then refined consecutively by a lot of people like Newton, Kepler, and a lot of people. Euclid, of course, all of us study about it, called Euclidean geometry, and also they were see, you are able to see them, that he was even a good mathematician, right? And then telescopes. Just imagine in the periods of 1500, 1600 about telescopes, right? To look at planets, to look at celestial bodies. That is what Galileo, I think in the previous image, you can see him looking at something, see in this image. So that's basically some kind of a telescope that he had done, or they had done something. So these are I would say these are very few achievements that he has done. He has a much more longer list of, you can anytime go and check that on. So let's go ahead with this. Now we have fast forwarded a bit. We reached to someone called Leibniz and Newton. So Newton is, of course, the very famous, celebrated god of physics. Leibniz, who is Leibniz? So Leibniz was actually a mathematician. Okay, he was actually a mathematician, and there has always been a controversy between Leibniz and Newton about who gave or who actually, did the mathematics of Newton's laws. The Newton's laws of motion. Who did the mathematics of it? So few people say it's Leibniz and Newton borrowed it from him, and few people say Newton did it himself. So that is not something that we are yet to discuss over here. That's a still going on debate. But what I feel is, I mean, the best way, the best thing to go along is you give the credit to both of them. Like, okay, yeah, come on, both of you did it very good. Thank you for that. So what did they do in mathematics? They did something. They brought out something known as the calculus. Okay, I don't know how many of you have heard this name. I think all of you are in, I think, maximum 10th or 11th grade, if I'm at the maximum. So I don't think you would have heard the name of calculus by now, and you will be anyway doing it later. So I will not get into what is calculus, but you can look at down. I have given a statement that it's a mathematical tool to understand almost, but no, it's not almost everything that's happening in and around you right now. It's only because of calculus. okay, in some or the other indirect formats. It can come through physics, it can come through chemistry, it can come through any way, but it is only, I would say it is 60% because of the mathematical tool called calculus. So this was the contribution, I would say a joint contribution of Leibniz and Newton to the world of physics in around 1600s. Okay, let's go ahead. So what is LNM? So LNM is nothing but Newton's laws of motion. We just abbreviated as NLM. So what does this do? What do we understand in Newton's laws of motion? Or what do we try to learn try to understand? This is highlighted in red color. This is a branch which deals with the laws governing with the motion of objects and their implications. Okay. Just pay attention to these certain things that I've put in red color, because they are going to construct the pillars of that building that you just saw a couple of slides before. Okay. So the first one, that is Newton's laws of motion. What are we doing with Newton's laws of motion, or what does Newton's laws of motion do? It just tells us, or it tells us the laws of motion which every object obeys. Okay. So what are the three laws? I mean, there are three laws of motion and we know them. The one is called law of inertia. What is law of inertia? Very easy statement, but not that easy to be understood. The statement is very simple. You keep a book in front of you and you don't do anything, the book will stay there forever and ever and ever. Okay, that's a law of inertia. Okay, you keep sleeping, you feel very lazy to get up in the morning. Okay, that's inertia because you want to continue your sleep. You don't want to get up. Okay, so that's a law of inertia. An object will continue to remain in a state of motion unless and until there's an external force applied to it. You can take the force whatever you want. You can take the state of motion whatever you wish to. The whole point is, if you need to change some object's position or velocity or some quantity or some physical quantity of that object, you need to do something to that object. That is nothing but the law of inertia. Okay, what is your second? Okay, so there is some mistake in this numbering over here, so please pardon me for that. So second one is, there's no name of this law. I have just put a name called maths of one. Okay, because that exactly it is. It just says F equals ma. I mean, all of you know the second law is F equals ma. I don't know whether you know a name for it or not. Okay, it looks very simple, right? F is ma. What's the big deal in that? So I have put in a bracket. The whole of physics lies here. Yes, it does lie here. You will see that at the end of today's lecture, after all the four pillars are done, there is still a lot to be done just using F equals ma. Okay, so this is the second law which actually governs everything in and around us in our daily life. Okay, and the third one is action reaction. I mean, come on, if someone comes and wakes you up from a deep sleep, you are definitely going to get angry, right? That's an action and reaction. Action was waking you up. You getting angry was a reaction. Okay, so every single thing in and around us will have an action and a reaction. This is nothing but Newton's third law. Okay. So what's so intricate about this? What is so intricate about this? What's so special about these laws? Right? Okay, just three statements, right? How is it different from what we are going to learn or what we see every day? You can read this slide. I'm not going to read it. But all I'll tell you is what's so special. Okay, before I tell you what's special, let me give you an analogy. Try to remember, try to think about this. Do you see air or do you feel air? What are your answers for that? Any answers?
They're saying feel. All of them are saying
Okay,
feel.
cool. You people, all of you can feel air. Okay, good. So tell me something that you can see but not feel. Can you feel light or can you see light? I'm sure you can see light, right? You can't feel about it. You can't feel the photons hitting your body, but definitely you can see your hand because of the photons, right? If you look at everything in and around you, you are able to look at it. You are able to see something. You are looking at a car moving, right? You are sitting down on your chair right now, listening to this webinar. The wind blows. I've given these examples in the second point. These are called effects, right? These are effects. The car is moving because of something. It's moving because of a petrol inside. It's moving because of some engines inside. Okay, but you don't see the engine. You don't see the petrol. You see the car moving. Okay, in a very crude manner. These are called effects. Okay, but how do these effects come? That was exactly what I said a couple of slides before. These effects happen because of some causes. Okay, you don't see the cause. The cause is generally hidden. Okay, you do not observe the cause of what is it. You don't see the cause, you see the effects. Okay, that is our general experience. If you look at the Newton's second law, F equals ma, I think I have written the fourth point. The F equals ma is a relationship which actually connects the cause and effect. Okay, a is their acceleration. I think all of you are familiar with what is acceleration. If not, it's not very big deal. It's just a derivative of velocity. Okay, you just have, you are moving, you're accelerating. You can take it in such a way. If you're moving faster and faster, you are basically accelerating yourself. Okay, it's basically the accelerator of your bike or car or whatever. That is acceleration. But that's an effect. You press the accelerator, your car goes faster. That's an effect. But why does it go faster? There should be some cause, right? That cause is not seen. You don't see the cause. You don't see why the car goes fast. This Newton's second law, F equals ma, tells you why it goes. That is nothing but the force F. So the force F stands for the cause and the A stands for the effect. They are connected with another property of a body called the mass of the body. It's very simple. You need to put so much of force to push a 10 kg object than to push a 1 kg object, right? That's the reason mass is being multiplied over there. It's not being divided. Okay. So any doubt over here in cause and effect as of now?
Uh, if you guys have any questions so far, what he's discussed, you can ask in the chat box. Else, we will move on.
Okay. I think I'll move on.
Also, one thing, there are some questions coming in. I mean, even before this, we will answer all these questions at the end. But if the question is specific to what he has discussed so far, you can ask now. But all the other questions we'll answer it at the end for sure. None of your questions will go unanswered. Do not worry about it. I'm noting down all the questions.
I'll proceed. I think I'll do
Yes.
that maybe. Okay.
Yes. Yes.
So where do we get to see Newton's laws of motion? I just said you. Where do we get? No, the question is wrong. The question should have been where don't we get? Because you look at it everywhere. Okay. You have Newton's laws being obeyed at every single place in the whole universe, at least in and around you. Forget about the whole universe. We'll come to the universe later. In and around you, you do not have anything which Newton's laws cannot explain. Okay. So let's come to some conclusion on Newton's laws of motion over here. And of course, your doubts are always there. That can always be answered. So so this is Newton's laws of motion. Very crude, very easy to say, but the most difficult to understand. Okay, they are Newton's laws of motion, practically applicable everywhere in and around you. That's Newton's laws of motion. What else has he done? Well, yes, he has done a lot of other things. He has done the gravitation. All of you are familiar with the Newton's law of gravitation, right? That is something he has again done. And optics. Okay. I will not dwell deep into it because I have other more 3 pillars to go on. I have just mentioned one slide about it. So this is your Newton's law of gravitation, a very famous image that all of you would have seen somewhere or the other, or at least seen the formula somewhere. And you can see the telescopes and other things that Newton used to do and all the prism. And of course, this is not right. This is not definitely the image of Newton's time or something, but you can definitely get the feel about what is it. The third image is something called as a Newton's reflecting telescope. Okay, current telescopes that we generally use in astronomy are generally refracting telescopes, but even we still use reflecting telescope for certain reasons, and they have their own pluses and minuses. So Newton was the first guy who actually came up with the concept and idea of a reflecting telescope. So that is about Newton's other works, but there is something that's still pending. Look at this slide. Was all perfect? No, they weren't. They weren't perfect in two senses. One, Newton's laws of motion, as I just told you, are applicable everywhere in and around you, right? But they are not applicable at certain points, at certain at certain situations. We will not be discussing those situations broadly today. And even the other case, that is the Newton's gravity, the theory of gravity also had a problem. You can see the problem I have posed as a question over there. How is the force of gravity being transmitted? Newton said in his theory of gravitation that there will be a force of gravity between two objects having so and so mass and so distance. That is what Newton had told. But when the Royal Science Society had posted and asked him a question about how is this force of gravity being transmitted when the bodies are not even touching each other? Okay, you are currently sitting on your chair, you are resting on your table, you are touching the chair, you are touching the table, so that makes some sense. But the earth and sun doesn't touch each other, right? The Pluto and earth, or Pluto and sun, the sun and moon doesn't touch each other. So how is the force of gravity being explained, or how is it being transmitted? Now this question was asked in 1600s when Newton had posted his theory, and he did not have an answer for it. Even then he just said, I don't know, this works, that's all. We have an answer for it today, we will see to that later, just keep following. Okay, any progress? Yes, we have done one. We have done Newton's laws of motion. We have three more pillars, so you can see the question marks on other three pillars. Let's go ahead with this. Okay, where do we head now? We are heading towards the second very important area of physics called the thermodynamics. Okay, this is called the thermodynamics. You are definitely sure, I mean, I'm pretty sure that you have been hearing the name of thermodynamics and this and heat and all those things. We will see what is this thermodynamics again. Let's go on to thermodynamics. What is this now? Okay, as I told you, the red ones are important. So thermodynamics is a branch that deals with the energy transfers happening in the form of heat between systems, surroundings, and the universe. Okay, it looks very complicated. Let me give an example. All of you drink coffee, right? You drink coffee, tea, hot water, you drink something. You drink cold coffee, you have an ice cream, right? You have ice cubes at your home, right? What happens when you take them out? You take an ice cube, you just keep it on your table. Does it remain solid? Does it remain cold? No. You look at the ice cube after half an hour, there's no cube. There's just water, right? There's just water. You take hot coffee, you come to your room, you leave the cup, you forget, you get into some studies, you forget about the coffee. And then you remember after half an hour, would you like to drink that coffee? No, because that's become cold. Why does it become cold? Why does the ice become water? Okay, such kind of things are dealt with thermodynamics in a very primary stage. So let's go ahead with thermodynamics. Again, see, there are laws in thermodynamics. We will not get into all of these laws again and again. I have just mentioned them. You can definitely read them. There are four laws of thermodynamics, the four primary laws of thermodynamics. Just like how we had three laws of Newton, we have four laws in thermodynamics. That's called zeroth, first, second, and third. You can see I have mentioned it saying crudely and crudely in the second and third law because that is not exactly what it says. That's little more deep, but we will not get into that deepness today. It's just to tell you that something exists and such things exist. So zeroth law says that yes, you have, you define temperature. We use temperature every day. Okay, what's the temperature of the room? What's the temperature of the city where you're staying in, living in? But what exactly is temperature? To be frank, temperature has no definition. We don't know what really temperature is. We define temperature on different contexts based on different systems. These four laws define temperature as per different contexts. That is what I have given in this slide. The temperature, the definition of temperature varies as per what context you're referring to. Okay. So we will look at this later. So you can just go through this slide if you really want. And I have anyway taken 4 slides of this as statements. So you can just look at them. We will go. So you can see there are temperature scales. There's something Celsius, Fahrenheit, and Kelvin. These are the mostly three used temperature scales. So Celsius and Fahrenheit are very, very popular. They are your everyday life measurements. We don't measure our city temperature in Kelvin, right? We don't measure our body temperature in Kelvin. You go to a hospital for a fever, you don't measure how much Kelvin is your body. You measure some Celsius or Fahrenheit. That's the max you do. Okay. So Kelvin is mostly a laboratory unit. It's mostly a scientific unit. whereas Celsius and Fahrenheit are more day-to-day life and more practical units of temperature. Okay, I have given a little bit of introduction to the laws. Okay, zeroth law. You can see the cartoon that I've done down. I have given down. It seems pretty obvious when you look at the statement. I have just given that if A and B have same temperature, B and C has same temperature, A and C will have the same temperature. It looks very stupid, right? And that's exactly what the cartoon portrays. But hold on, it's not that simple. Again, I cannot take a detailed class about why it's not simple, but it's just not simple. Okay. But yes, in your practical day life, it is very easy to understand this concept. So zeroth law says that if you have two systems, A and B, some systems which have the same temperature, and if B and C has the same temperature, then A and C without being in contact will also have the same temperature. That's about the zeroth law of thermodynamics. And yeah, you can look at the cartoons for more interesting stuff. So that's all right. Now there'll be some equations in between. It's your wish to pay attention to them because it is actually no way connected to what we're discussing. It's just to tell you that yes, there is something more than statements. Okay, so this is the first law. First law tells you what is heat and what is work of a system. Okay, so this equation that's right in front of you in pink color, it's delta U is some Q minus W. We will not get into the details. Delta U is the something called as the change in internal energy. Every system will have some energy within itself. You people have some energy right now within you. Okay. You can charge up that energy drinking something, drinking coffee, or getting some fruits, or having something. That is a charge. That's a charge up. Okay, that is something you give to your body from your outside. But there is something inside your body. Your heart is pumping, you are breathing right now, you are attentively listening right now. You need energy for that. That energy is nothing but the internal energy of a system. Q and W are heat and work. They are almost same, but not exactly the same things. We will not get into what is heat and what is work. You can just understand heat and work are two different forms of energy. Just like all of you know kinetic energy and potential energy, all of you know electric energy and magnetic energy. It's just like similarly you have heat and work. They are just two different forms of energy in two different contexts. Okay. The second law states the directionality of heat flow. Okay, we know that energy will flow. All of us know energy flows. We know water flows, right? You go to a waterfall, the water falls from the top to bottom. In your home, the tank is always placed on the roof so that the water can come easily without any motor from the top to the bottom, right? So there you can say gravity. That's an explanation. But in general everyday life situations, in thermodynamics, gravity doesn't play such a huge role. Here, the second law comes into picture, which tells you quantitatively about how does the heat flow, what is the direction? Will it flow from hot to cold? Will it flow from cold to hot? That's the reason you keep a hot coffee, it becomes cold because the heat flows from a hotter substance to a cooler substance. Your room temperature will have a lower temperature compared to your coffee. So hence the coffee loses the heat. Similarly, when you put your ice outside the freezer, ice has a cooler temperature than the room temperature. So the room temperature heats up the ice. That makes it to melt. That is because of the second law of thermodynamics. There's another way to look at second law of thermodynamics. There are so many ways to look at it. One of the major reasons or the application of second law is your heat engines, your bikes, cars, ACs, fridge, all of them work based on the principles of second law of thermodynamics. We will not get into, again, we are not getting into the details of all of these things, how they work. The third law. This is a very, I don't know how do I put this law in a very simple term because this is a very mathematical statement. So I will not try to even explain because if I try to explain, people generally understand it in a wrong way. You can all understand this way in the worst case scenario, you can just, have in mind. Third law states that if the temperature is zero, an object will have zero, the entropy will be zero. Now, what is entropy? That's the next slide. Okay. You can basically understand entropy as the motion of atoms and molecules inside a substance. That's called entropy. How how randomly are these atoms and molecules moving in and around, or the electrons moving in and around in substance. So at 0 degree Kelvin, I'm not saying about Celsius, at 0 Kelvin, there will be absolutely no movement of any atom or any molecule or anything inside any substance at 0 Kelvin. That is what the third law says about. Yes, what about N? N is nothing but entropy. I just said entropy is nothing but a number of how randomly a system can be arranged. How many random motions can an atom do? Can it go front, back, left, right, top, bottom, somewhere in between directions? And similarly, not just one atom, but so many billions of atoms. That's called an entropy. Okay, you can see it gets a little bit intricate, so we'll not get into the details of that, but this is essentially what the third law says about. Who did all this? Well, Newton did Newton's laws of motion. Who did thermodynamics? Unfortunately, it's not one guy. There are so many people who did thermodynamics, so many people, and I have just given a couple of names. Okay, Galileo, Newton. Yes, see, Galileo again has given his contributions to thermodynamics. You can see Joule, Planck, Newton, Gibbs. So many other people have given. Okay, you will see this Maxwell. The last name I've written is Maxwell. You will see his appearance in the next context also. So yes, this was about thermodynamics. Are we wet? No, we have two more. So now, by now, there are two pillars that you have understood, that you have learned about, that you have heard about. One is the Newtons, one is thermodynamics. Now let's go to our third one. It's electromagnetism. Okay, it's about electromagnetism. Before I start electromagnetism, any doubts on thermodynamics? Any questions on thermodynamics that I just took?
There is one question.
Yes, now?
During the second law of, this is from Shirvain. During
Yeah.
second law of thermodynamics, you told the water tank is kept in top of the house or structure for gravity,
Yeah.
but isn't it for pressure?
Exactly, it is for pressure. If you look at the pressure, it's actually the potential energy. You know, you go for pressure. What is the relationship for a pressure? I mean, which grade are you? Can I use formulas? Can I use formulas just in case?
Shivan, which grade are you in? Seventh.
Seventh. Okay. So I think you must have heard about this formula called P is equal to rho GH. Pressure is given as rho G and H, right? So H is the height, G is the gravitational, I mean, acceleration due to gravity, and rho is the density of water, right? So definitely that H, that height matters. If your height is zero, that is, suppose the tank and your tap are at the same level, okay? The height is zero, so the pressure will be zero. You will not have any water kind of thing if the water level in the tank and your tap is exactly the same level. I'm not talking about the height of tank. I'm talking about the height of water from your tap. If the water and your tap are exactly the same level, there'll be no flow. There'll be no flow of water from your tap. The height matters. The height gives rise to pressure, which is indirectly you can take as in potential energy. So we say more the height, we say more the potential energy, and hence more the pressure. Okay, so you can connect in that sense. It's not exactly that, but you can connect in that sense. But yes, second law of thermodynamics is not dealing with any pressure or height or something. This is entirely different. This is just to state an analogy or the flow. There it flows from a higher height to a lower height. Here it is flowing from an hotter object to a cooler object. That is all I'm talking about, the analogy part. Is it clear to him?
He's understood. He said he understood.
Okay. Anything else? I'll proceed ahead.
You can proceed ahead,
Okay, now.
Sameeran. Yeah.
So we have the third pillar we'll be learning about is electromagnetism. What is electromagnetism? Again, the red one. This is pretty long, but okay. The second part is an application. After the full stop is an application. So what is electromagnetism? This is a branch which deals with electric and magnetic interactions between particles. If you look at an atom, all of you know that there will be a nucleus and there will be an electron. The interaction between the nucleus of the atom and the electron is an electromagnetic interaction. That is not because of gravity. Of course, there is gravity over there also because even they have masses, but it's very, 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 very small. If you compare with the electromagnetic force and the gravitational force over there is highly negligible. It's not zero. Of course, it's not zero, but it's highly negligible. Okay, so electromagnetism is a branch that deals with the electric and magnetic properties and interactions between two charged particles. I'm sorry, I forgot to write the charged particles. That's very important. If you do not have a particle, if you have a particle with zero charge, it will not interact in any electric and magnetic fields. So I'm sorry about the charge thing. It is electromagnetism only arises when you have charged particles, but gravity doesn't care. Gravity needs mass, and if you have a mass, you are in gravitational force. But electromagnetism requires charge. Okay, and the reason currently we are able to host this session, you are able to listen to me, I am able to share whatever I know, it's only because, of course, it's because of internet, it's because of fast internet, is because of all these communication techniques, and communication techniques solely relies on electromagnetic waves that we are going to anyway come across in a couple of slides. How did this start? I think all of you have heard the story about the electricity. I mean, lot of centuries before, when it used to rain, when there used to be thunders, lightning. That time, people used to think that this is some kind of a supernatural, somebody is really angry up there or down there, and hence they are giving us such a punishment. Okay, this was the way how people used to figure things out when the science, when the physics was not so evolved around it. Okay, so that was the place, or that is where people actually started to realize that there is something happening, there is some intricacy between what's happening up there and what happens down here. Of course, today we know that lightning is nothing but discharge of current or discharge of electricity in the when the clouds get excess of charges. That's what we know today, and that's how electricity, the concept, the ideologies of electricity had begun from. Magnetism has an entirely different story. I don't even know if this story is actually true, but I have only come across this story as per what I remember. So you have this shepherd who's going, or who's taking this thing somewhere, and then he suddenly happens to observe that his stick gets stuck to a rock. It gets attracted and gets stuck to that rock very hard. He had to put a lot of effort and labor to actually pull out that stick. So at that point of time, he was very much shocked, because how did this even get attracted over that? Okay, that was the advent of magnetism, from where this magnetism started, and how people started to look at this area. Oh, okay, there is something existing like this. That is how this started. A little into them. What is primarily electricity and magnetism? They were in the very beginning, as I just told you, something is being thought of thunders and lightning, whereas something is being thought of some rock and some attracting some sticks or something. If you, or if I and you and all of us would have been born at that period, we would generally not try to even think about stating that these two are probably connected to each other, or probably some kind of relationship exists between these two phenomena. A phenomena that is giving us lightning, and a phenomena that's attracting my stick, right? There would have been nobody even would have guessed about it, right? So they were completely thought of two different forces that were working around. But again, just like thermodynamics, we have a lot of other people working in. We had, had been working in electrodynamics, electricity, and magnetism, who actually helped us to understand that no, these are not two different forces; they are the same forces. We will be looking at them in the coming slides. Here, there is something called as a concept of field, which I will not actually take because that will take a little more time. So all I would say is the field concept simply says that there is a presence of something in space, okay, in and around you, which is not physical. You cannot see that, but there is, you can feel that. Okay, it's basically like you go to your schools after COVID is done, and if your teacher is sitting in the class, before you enter the class, you enter in a very disciplined manner. Okay, but if the teacher is not there, you enter jumping, rolling, or whatever you want, you can enter. You have a freedom over there. But when the teacher is sitting there, you cannot just roll in and just get in your class, right? You will have to go in a line or something, and all those things. Why is it so? It's because there is a teacher inside, there is somebody sitting inside, and that because of that, there is some effect. You are facing some effect. You're not able to move as per your wish. Okay, that's because of a field. Okay, You don't go and touch your teacher and then you start rolling. No, you automatically start, coming in discipline right from the door. That is some effect. That is a field. That is a field. Okay. So that is how electric and magnetic forces propagate. And these are some formulae, and just like how I gave for Newton, these are just some formulae and some diagrams about how the electric field lines look like. Okay, you need not get into this so much. This is just a slide to give you a completeness. These are all just like how we had Newton's laws. We have here something called as a Gauss law. Okay, this is a law used in electrostatics for electricity. Similarly, you have for magnetism, this is the formula for magnetic force, and these are the fields of magnetic forces. And you have a law in magnetism called the Ampere's law, just like Newton's law, just like thermodynamics, the laws of thermodynamics. In electricity magnetism, you have Gauss law for electricity and Ampere's law for magnetism. That is all about these slides. And you have little more contribution from Faraday and Lorentz. So these are two other great people who have done a lot of things in electricity and magnetism. Faraday and Lorentz were the first people to experimentally demonstrate that electricity and magnetism are not two different things. They are the same thing experimentally. Okay. They are the pioneers of this. And finally, we have Maxwell, the guy who actually mathematically wrote down the equations of electromagnetic forces. These four are the equations. You need not get into what these equations are. All I'm saying is these four equations summarize the entire electricity and magnetism going on in the entire universe. Okay, just these four equations tell you about them. All of you have learned about light. All of you have seen, all of you are able to see these things because of light. Light itself obeys these equations. Okay, that's why I've written down optics starts from solutions of Maxwell's equation. Light is all about optics, and optics is nothing but a solution of these four equations that's right in front of you. So we have done with three pillars. What's the last one? I think you people are slightly bored, but yes, don't be. This is the most interesting one, which will actually blow off your minds, that I've written on the slide, which is quantum mechanics. Okay, all of you are familiar with this title, with this name, and probably with a lot of videos on YouTube on what is quantum mechanics, how weird it is, and etc. 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 They are always there on YouTube, so let us check on them. So I have given a bit of introduction to what is quantum mechanics and why and everything. How did it start? I cannot get into the details of how did it start, because if I had to include them, I had to take up 100 slides. So forget about that. All you can do is you can really understand that quantum mechanics began after Maxwell's equations. Okay, that is where quantum mechanics actually started its journey from. Who are the quantum mechanics parents? There are again a couple of people. It's not just like Newton and Galileo. There are I would say hundreds of people. There are literally hundreds of people who have actually given their lives to develop quantum mechanics. Okay, I've just given a couple of 10 or 7 or 10 names over here, including radioactivity. Madame Curie, Marie Curie. She also, the laws of radioactivity are also explained using quantum mechanics. Okay. What does quantum mechanics say? The red one again. Quantum mechanics is a branch of physics which denies logic. You cannot apply logic to quantum mechanics, my friends. You cannot do that. You can say Newton's laws of motion are applicable to logic. You take a stone, you throw it, the stone is bound to hit the ground. The stone will never disappear or go somewhere. It is not going to reach to the moon unless until you point it towards the moon with a rocket or something. It is going to hit down according to Newton's equations. But no, quantum mechanics says no, it cannot be. You point a stone right from your roof to the ground, you might find that stone next moment in the moon also. That is what quantum mechanics says. Okay, it denies logic, it denies common sense. It makes sure you don't try to understand it, rather just sit and work it out. That is exactly what quantum mechanics is. You cannot try and start logicking out that, see, quantum mechanics works this way. No. The moment you try to understand one problem, that, okay, this is how it worked, the other problem, the whole rule is reversed. You will be like, okay, wait, This just worked right now. Why isn't it working right now? That's quantum mechanics. Newton's law will not do that. Thermodynamics will not do that. Electricity magnetism will not do that. But quantum mechanics will do that. That's what I've written in the second sentence. The fathers of quantum mechanics has not been able to interpret it properly. The people who literally wrote down quantum mechanics stated that we don't understand it. Okay, so that's how profound quantum mechanics is all about. See, these are the weirdness of quantum mechanics. You can look around. There is no definite position and velocity for an object. Come on, man. We are every day seeing our bikes and cars moving with 30 kilometer per hour speed, right? But quantum mechanics says no, there is nothing called 30-kilometer exact. That's quantum mechanics. All particles behave like waves and waves behave like particles. What nonsense is this? You throw a ball, it will not disappear to some other universe just because it's a wave. The ball is a ball, it's a particle. That's it, right? That's Newtonian mechanics. But no, quantum mechanics says no, that's not how it is. An object can be in one or more places at the same time. All of you are right now listening to me in this webinar sitting at your home. You cannot exist sitting at your home and your relative's home right now listening to the same lecture at the same time. That's impossible. But no, quantum says no way, that is possible. And yes, it has been proved right. It has been proved right that particles can exist in more than in more than one place at the same time. It has been proved experimentally in the past couple of years, including a recent, I think, just a couple of months before also. Reality doesn't exist until someone looks at it. Yes, this is what quantum mechanics says. It's basically like you don't look at the moon, so moon doesn't exist. Well, Newton will say that's stupid, but quantum mechanics says no, that's equally valid. If you don't look at the moon doesn't exist. As simple as that. That's quantum mechanics. You can see the rest of the two options. It's basically weird. Okay. So are we nuts to believe them? Are we? Are we so dumb to believe them? Probably yes and no. We don't know. It's yes and no. We don't believe them because they are weird. We don't believe them because they are very, very, opposite to what we think about. But we should believe them. We are bound to believe them because till date, quantum mechanics has never ever has been wrong in predicting any particular outcome. Quantum mechanics till date has always been proved right in any and every experiment. In any and every experiment. Okay, that's quantum mechanics. It has been proved right in any and every experiment, anywhere and everywhere, anytime and every time, till the birth of it. It's more than 120 years or so it has been born. Till date, not even a single experiment has denied the laws of quantum mechanics. Hence, we are forced to believe it's true. But how? Let's not answer this because we don't know how. We really don't know how. People who formulated quantum mechanics don't know how. So so what can we do? Predict, formulate, solve, experiment, observe, compare, and if the results match, stay happy. That's all we can do, and that's exactly what we are doing. The results have always matched. Always matched. Not a single denial as of date. Okay. Hence, we are happy and we are learning about it. That's all we are doing in quantum mechanics. Yes, we have done. Almost we are over there in quantum mechanics. We have done the 4 pillars, but are we yet? Just a slide more. Just a slide more. As I told you, till now, we have seen what it started from and how weird quantum mechanics is. That has been the journey that we have discussed till now. But let me tell you, we are not here. We have gone way more ahead in the past 20 to 30 years. We have gone way more ahead of quantum mechanics. That's exactly I've given the next flow chart. This is a flow chart of your, the most, the most trending or the most important branches of physics. The arrow marks might be weird, something up and down, left and right, but I'm sorry, I have no other go because I cannot isolate any branch from other branch just as a singly standing one. All the branches are interconnected. You have branches which has come up from combinations of more than 2 or more branches, and hence I had to show it this way. But this is a very, a very crude way of looking at how physics has evolved, how it has diverged over centuries, where we are right now, and what are the challenges, what are the areas that's left out to explore in the coming days, in the coming years. I have written there, where do we stand? We stand here in that black color thingy. We have written there, we stand at the junction of something called as general theory of relativity, that is GTR. I have written the abbreviations in the left bottom corner. GTR and QFT, something called as the quantum field theory. Quantum field theory is one step ahead of quantum mechanics. There are certain questions of quantum mechanics which had not been answered, which has its answers in quantum field theory. Not all answers, but some answers in quantum field theory. Today, we are trying to understand, we are trying to merge gravity with quantum field theory. That leads to down to the um, things I've written, string theory and loop quantum gravity. These are all the theories, these are all the speculations that is currently going on in active research in physics, which is having the aim to unify gravity with quantum field theory. Once we do that, we reach one grand unification. We will have one single law, one single expression, one single formulation for the entire physics that we have understood till date. Okay, that is exactly what grand unification is, and we are not yet there. We have to go there. So I hope that, many of us, many from you people, will grow up, will take up this and be one of the contributors of this grand unification. And probably generations later we'll be studying your names, just like Newton, Galileo, Maxwell, etc., in contribution to the grand unification theory. Okay, there might be doubts, you people might have doubts in what is this QCD and QED and all, but I will answer them provided you take them up in the Q&A session, because I think the time is I think sufficient for Q&A. So Obliana, I think should I end here, should I continue something? I think this is
Yeah.
the end of my slides actually.
Okay, then I think we can open it up for
Yeah, you can
questions.
open up for Q&A.
Yes, thank you, Samir. That was a very interesting session. And kids, if you can ask questions on the topics that was discussed today, Samiran will try to answer them. You can please type in the chat box, or you can raise your hand so I can let you.
Obliana, where do I actually look at this Q&A actually?
I'll read out the
Yeah,
questions to
yeah,
you.
okay, then fine, then fine.
No problem. Yeah. So yes, you can ask your questions. I'm waiting to read it out to Samiran. I think there was one question in the beginning. I think if uh,
Yeah. There was something. I think
I
after thermodynamics, I guess.
yes, I think it was asked by Malik. Malik, are you still there? I don't know if Malik is there. Okay, others, you can please ask your questions. Is the flow chart? This question is from Harshan.
Yeah.
Is the flow chart like zeroth law? Everything is interconnected.
Sorry. The
Is this
flow chart
flow
is.
chart, that the one that is showing right now,
Yeah.
is it like the zeroth law? I think he's referring to the zeroth law of thermodynamics. Everything is interconnected. Is that the meaning of it? Like he's asking.
Well, yes, you can take. I mean, zeroth law doesn't say everything is interconnected, actually speaking. But yes, the flow chart definitely says that. Zeroth law doesn't say about the connectivity of anything or something. It is about. It is very specific to systems. Zeroth law is generally the formal definition of a temperature that we look at everyday life. That is all about zeroth law. But yes, the connectivity part, definitely the flow chart is connected. I mean, you cannot isolate any branch from it. You can see. I mean, I have tried my best to branch out separate things. I mean, you might have some doubts on what is Lagrangian in under that Newtonian thing and all, but I will not go into those things. They are just the departments, they are just the areas that is right now well understood, it's well in there, and they are diversions from Newtonian mechanics. As I told you, Newtonian mechanics is right, is beautiful in our everyday life, but that is not working, or that doesn't work when you go to at different ends of the universe. So you have different laws, you have different principles working over there. Okay, so that is in relativistic. I have written in the red color down. You can see that we haven't spoken STR and GTR. I mean, I really can't do that because that will take another 50 or more, maybe more than 50 slides. So that's not possible. But yes, yes, according to your answer will be yes. All these branches are interconnected. I mean,
Uh,
it's way more complicated than this.
yes, so next question is from Nivriti, if I'm pronouncing the name correctly. What are the applications of quantum mechanics?
Okay, I actually wanted to give a slide on that, but it was getting much more. So applications of quantum mechanics is very difficult to say where it is not being applied. Right now, in your mobile phones, I can give you the best example, electronics, right? Any electron, let it be a mobile phone, your computers, your laptops, washing machine, TV, fridge, whatever electronics, all of us know they work on microchips. There is some program, there is some, there is something going on inside a microchip. The memories, all your 64 GB, 100 GB, whatever GBs is, they all have certain microchips. Those microchips are nothing but, they are byproducts of quantum mechanics. That is, they are electronics. They are basically electronic items. Electronics are nothing but semiconductors. They are not, you of course, you don't have microchips made out of copper or aluminum, right? You have them made up of silicon, indium, gallium, and those. They are called semiconductors. They are not metals. They are not non-metals. They are called semiconductors. Okay. The semiconductors, the whole branch of semiconductors, about how does a semiconductor work, how does a conductor work, is based on the laws of quantum mechanics. So quantum mechanics is the guiding principle to the construction, to the development of semiconductors, which helps in the development of electronics, which is what we are enjoying is in the form of laptops and everything in and around us. So as such, I would say you cannot see quantum mechanics in front of you, but yes, these things are possible because of quantum mechanics.
Okay, thank you, Samiran. We have some more questions. One question is, what is string theory? I think you can tell very briefly if you can. What is string theory? Yes, would you like to answer
Yes,
that?
I will just say as short as possible. So,
Yes.
string theory is basically a theory that is trying to unify gravity, that is not Newtonian gravity. It is trying to unify the Einstein's gravity, which is nothing but the general relativity, along with the quantum field theory, which is a step ahead of quantum theory. We haven't spoke about this QED and QCD and all. So after quantum theory, you have something called as QED, which I've given in the left side, called quantum electrodynamics. There's something called as QCD, called quantum chromodynamics, and they constitute an EW, along with something called as EWT. These three things constitute quantum field theory. Okay, this quantum field theory and trying to merge this quantum field theory with the general theory of relativity, which is the Einstein's picture of gravitation, is what string theory trying to understand. So string theory is a approach, is a theory, it's an approach that is trying to merge the Einstein's general theory of relativity with the quantum field theory. Okay, that is string theory. I cannot go beyond this for string theory.
Thanks, Samiran. Next, we have uh, one more question. I mean, we have few more questions. So, how far? Like, I'll combine to two questions. Okay,
Yeah,
I'll
yeah.
ask one question. So, one it's from Srivatsan. Is it proved that if we come near to the speed of light, the time slows? Then can we travel back in time if we travel faster than light? So that is a question from Srivatsan. You can again answer it briefly without not getting too much technical.
Yeah. Well, the first part of your question, yes, it is proved. Of course, it is not proved by a human being traveling close to speed of light, because you very well know the even the rocket speeds are way, way, way less compared. It's like unimaginably less compared to speed of light. Okay, even the fastest rockets. But yes, there are experiments, there are applications, there are data that suggests that if you are very close to speed of light, the time actually slows down for you. Okay, or for the particle, or for that object which is at very close to speed of light, there are laws, which is nothing but STR. That is exactly what STR is about, which I've written there. STR is special theory of relativity. So STR stands, or STR tells you how objects behave, or what happens to the time, what happens to their length when they are traveling at very high speeds. That is the first part of your so yes, it is proved, it is right that time really slows down. The second part about time travel and all, well, personally, I don't know much about it, and I don't think it is possible because STR doesn't allow it. The physics of special theory of relativity does not allow time travel. But I don't know if there are any experiments or details which has been proved or something. I am not sure about that part. But according to the physics of STR, it is not possible. You cannot go either to the future nor to the past. That's actually not possible. In principle, it's not possible. You can, of course, have thought experiments. You can have paradoxes. That is something different. But in principle, I don't think it is possible personally. So yes.
Okay. Thanks, Samiran. We have next question, which is, um, okay, is there any connection between quantum physics and theory of everything? I think that is related to the previous question. So,
Yeah, you can see the relation. It's right on your screen. I mean,
yeah,
not a direct relation. That's all I can say.
yes. So I have one question from Harshan, which I think probably will take it at last, but I'll just read it out. How can quantum mechanics exist without logic? Everything has logic in it. So that I think that we'll take that question to be the
Yes,
last
yes,
question because
yes,
it is more interesting. But
yes.
in the meantime, I'll look for other questions. Oh wait, I think there are more questions coming in. In interstellar, time slows down because of gravity. Is this really possible? I think that is what Samiran answered just now. Yes, as the faster you travel, the time does slow
And
down
he's talking about gravitational time. This thing. It's
because
not
of
about the STR part, right? He's talking about the
because of
gravity,
gravity.
physics
Yes,
of
okay.
gravity and time.
You can talk
Yeah.
about that briefly as well. Yes.
Yeah. So yeah, your question is again Interstellar. Definitely, it's a beautiful movie, and yes, even those effects are correct. Of course, there we don't see the speed. I mean, there is nothing. I mean, when you're in a planet, the speed doesn't. There's nothing called speed, but the gravity matters, and that is a context of GTR. That's not comes under STR. That comes under GTR about how gravity affects the motion and time of objects. STR is about how speed affects the motion of time and objects. GTR is about how gravity affects. And yes, you are right. More the gravity, more stronger the gravity of an object, lesser or slower time the object will experience. That exactly happens when you go near a black hole and all other things because of gravity. They have very strong gravity. So yes, that is true.
Okay. Thanks, Samiran. We have next question. Just give me a moment. I'm just looking if I missed any question. Um, okay, so the next one is speed of light impossible to achieve? Because how can we get to zero mass? Everything must have mass, right? Except photons.
Okay, your answer is right in your question that if you have a mass, you cannot attain the speed of light. So if photons are particles, or probably they are particles, we don't even know they are particles or not. But if they are particles, they are massless, and hence they are traveling at the speed of light. The next closest guy is probably, I believe, is neutrinos. They are the next fastest things, fastest people on Earth. Literally, they are people on Earth who are traveling at such speeds, but not again. It is not exactly c. It is 99 point some 9999 some percent of speed of light, but it is not the speed of light because even neutrino has some very 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 negligible mass, but it is not massless. So if you have a massless particle, it will travel at the speed of light. If you have a particle with some mass, it is impossible to achieve the speed of light with a particle having some mass.
Okay, thanks. I hope that answered Shivin's question. Thanks, Samiran. Guys, if you have more questions, you can type in. I'm just looking at anything that I missed. Okay, one question that I missed was how far away are we from unified theory? Or
um, we are pretty far away. That's all I can say right now. Because as I just said, the string theory and the last 2 to 3 boxes we have done, that we stand here, that is a very 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 new domain. I mean, it just started in 1970s. I would say 1960s. I would say I think all of you know this Nobel, right, just couple of days before the Nobel Prize of Physics was given to one of the scientists called Roger Penrose, if I am right. So this Roger Penrose is a very active. He has been a very active researcher in string theory. He has a lot of contributions to string theory, to the modern string theory. So string theory is a very new area. It's a very new developing area. So is loop quantum gravity and other. There are so many other competitors. I don't even know. I've just put three dots over there. They are all very new areas. So it just started in 1960s, 70s. So there's a long way to go. There's a long way to go for unified theory.
Okay, thanks, Samiran. There are some very like um, fundamental questions that are being asked, which are really difficult to answer. Harshan is asking, how can anything ever have no mass? And something connected to that, um, everything has atoms which have mass, and things like that. So, how can we have anything that has no mass?
Well, that's what I'm saying. That anything that is nothing which has no mass except photons, and we don't know what photons are. To be frank, at least I don't know what photon is. Some people say it's a particle. Some scientists say it's a wave. Some say it's none of them. And quantum mechanics says actually quantum mechanics says photon is none of them. Quantum mechanics says even electron is not a particle. Okay, that's what quantum mechanics says, and it is proved that is electrons are really not particles at some times, they are particles at some times. That's quantum mechanics. Okay, so as I told you, I think a lot of your questions are I mean, just as Anna read, a lot of your questions are the reason because it defies your logic. How can it not have a mass? How can it not go to this speed? How can it not happen? That is, it's because we think it should. We think it should, but it doesn't. Okay, it really doesn't. That exactly is what quantum mechanics. It's weird. It's very weird. It's very difficult to understand these things. Okay, there might be logic, there might not be logic, there might be reasons, there might not be reasons. We need to be very open to that, to accept that yes, there are certain things which is beyond our that's beyond our way to competence them. It's not that easy to say that it should be like this. Why is it not like that? There is something much beyond this, and that is quantum mechanics. So quantum mechanics says there's nothing called as an electron. Okay, that this is what quantum mechanics is, and it is actually true. If you when you study later, you say that atoms have orbits, you have electrons revolving around and those things. They're actually not absolutely correct. They have certain flaws, and that's proved by quantum mechanics, and that actually proves that electrons are not really particles that go in circles around the nucleus. They don't always go in circles. There are different ways in which electrons can go. They have been experimentally verified, they have been experimentally proved, they have been experimentally done and verified using the laws of quantum mechanics. So yes, these questions are difficult to answer because that's how our intuition works, but quantum mechanics doesn't follow our intuitions. That's all I can say right now.
Okay,
Yeah,
thanks,
even you
Samiran.
can add on to this.
Yeah, I'll add on. I'll just have a couple of observations, but
Yes.
let us finish the questions. So one more question. I mean, there are a lot of questions coming in. One question is it possible for humans to create a massless object? If we can create light. So in that sense, yes, we can create a massless object. I
Yes.
mean, it is not that. I mean, we cannot create a massless object in the sense that you mean, but if we are somehow able to create light, for example, in a way we are creating massless particles. So that is
Lasers are the
what
best examples of you creating a massless object. So yes.
creating light is what. Then we have, is it possible to generate energy and to discover new particles through hadron particle colliders?
Definitely, yes. I mean, that's exactly what we are doing for the past 30, 40 years. That I actually, to be frank, quantum field theory, the one that I've put in the gray box, that has been, what do you say, inspired by, people have been inspired to develop quantum field theory only because of the experimental data obtained from Large Hadron Collider due to experimental data of collision of protons and neutrons and those things. Because of them, the data were very interesting. The data was very very different from that were expected, and that actually gave birth to the theory of quantum field theory. So yes, that is exactly what we are doing. We go higher and higher energies, we collide particles at much and much speeds, and we try to see what comes out new from them. So that's exactly what LHC is doing.
Okay. Uh, are quantum theory and quantum mechanics the same? Yes, in principle, yes, same, Nivriti. They are essentially the same. Quantum theory and quantum mechanics. I'm just reading out other questions that I may have missed. Um, okay. I think I'm not missed any question. Have I missed any questions? You can let me know if I missed any of your questions. Okay, one of the question, are Einstein-Rosen bridges real, or are there possibilities for tunnel in space field?
Is he talking about the EPR?
Yes,
Okay.
Einstein Rosen bridges, like
Forrest
tunnel.
Roskin, I guess.
I think it's talking about the space-time warps connects.
So
Okay,
basically leading
Einstein-Rosen.
up to wormholes and something, if I'm right. So I don't know if I can answer that right now.
Okay, so Einstein Rosen bridges are in like a theory. They've not been found yet. Okay, so they're not real in that sense. If you're asking about it, okay. But again, I'm glad you've heard of these Einstein Rosen
I mean,
bridges.
exactly. I was thinking
Um,
about that.
so I'm happy that you at least hearing of these terms. Okay, so won't the particles give off energy when colliding with each other? Won't the energy be like the sun? Of course, they generate a lot of energy, Harshan. In fact, to make them collide, you need to pump in a lot of energy to make them collide with each other. And when they collide, they will give out a lot of particles that they are made up of. They reveal, and of course, it will generate energy as well. It won't be like the sun. No, definitely not. We are dealing with a very small portion of it, but again they will generate a lot of energy, but definitely sun has much more energy than we can generate here on the labs. But yes, we have very high
Temperatures.
temperatures and energies that will be generated in the hadron collider. That is true. um, I think that is the end of Yuvan says, even if you have mass and you had infinite energy, could you go to the speed of light? um, Yuvan is asking, even if you have mass and you had infinite energy, could you could go to the speed of light? Yuvan, no, that there is it is not possible. It is like a hypothetical situation that you're bringing in here, where you have infinite energy and also you have some mass. No, the problem here is your mass will increase as your speed increases or approaches the speed of light. So it's something that we have not talked about in this session because it's out of the scope. Your mass is not going to remain the same. As your speed increases, the mass of the object will also increase. So the more and more speed you try to achieve, the more and more massive the object will become, and more difficult it will become for us to increase its speed further. So in that sense, you can never achieve the speed of light. Okay, so and again, infinite energy is again. So if you get infinite energy, the mass will also become infinite.
Exactly.
The
Because
closer,
they
the
both
closer, the
tend towards
closer.
infinity.
Yes, the closer you approach to the speed of light, the mass of an object will also become infinity. So we have infinite energy and also have infinite mass. So the point is, the laws of physics like prevent you from achieving the exact speed of light, because you're going to become more and more massive, infinitely massive. So even if you go
Anna,
to
I just
infinite,
want to point out a misconception here.
yeah,
Uh, See, I mean, I think all of you heard about the STR, the special relativity, right? So there's a misconception. I'm just telling it out that many people believe or think that special relativity is a theory of photons or light. No, it doesn't. It is not. It is just a theory, or it is just a practical a thing of or related to the particles that are traveling close to the speed of light. Special theory of relativity does not hold for photons itself. It breaks down at photons. The moment you put the velocity of light in special theory relativity equations, the equations break down. You come down to infinity, just like exactly what you said, infinity mass, infinite energy, which is not admissible by physics. So special relativity is a theory for those particles which is traveling close to the speed of light, but not at the speed of light. That's actually a misconception I have actually come across in a lot of students.
Thanks, Samiran. Thanks for clarifying that. And Srivatsan, that question that you asked is way beyond the scope of this question. Are strange quarks with the highest surface tension dangerous? I'm not even sure if you actually understand what quarks are. These questions,
Exactly.
so these questions are like too complex. I'm not discouraging you from asking that question, but there are several levels, orders below that we'll have to start understanding before you come up with
Just
questions
to
like
tell
that.
him that you
Yeah.
will encounter quarks in the QCD domain. Once you enter QCD is basically the interaction of quarks.
Yes,
So
so
you need to
quantum
get some
thermodynamics is what
for
he
that.
is referring to. Yeah,
Yes.
so let me, I think we will stop taking questions because we are up 8:15, because, and I'm sure you're also hungry and we're also hungry, but let me make an observation here. So I see a lot of you are interested in this topic, and Samiran made the session really very interesting with these pillars, and that's holding physics, these four pillars. But one thing that you will have to understand is that do not get carried away by these the fanciness of this quantum mechanics, or how it defies these your intuitions and things like that. And one of your questions, like Harshan asked, everything has logic in it. Why is there no logic? No, there is logic. Okay, so let us be fair. And what Samiran was trying to say is that it is counterintuitive. So when I say counterintuitive, you think something, you expect something to happen, and that is not what quite something happens. So your results are not, does not make sense to you. Okay, but doesn't mean it has no logic or pattern. There is a pattern in quantum mechanics. There is a very at a superficial level, if you look at it, it might look like it does not have any logic or pattern, but underlying there is some kind of pattern. And to be very I mean, I'm not clear. I mean, to be very superficial about it, you can say there are probabilities. Okay, there are. I'm sure you've heard of this word chances, probability. Like probability meaning, if you toss a coin, what is the chance that you'll get a head or a tail? It's 50-50, right? You call it probabilities. So the entire quantum mechanics field is governed by probabilities. Okay, so nothing, you cannot tell something is going to happen for sure, but you can give probability. So you can say with a 90% probability that you can predict an outcome. So it is not like the quantum mechanics has no logic in it, but it has logic, but that logic is founded on probabilities, not with certainties. Like you cannot say 100% certain it's going to happen, but you can say with a lot of probability you can expect predict an event to happen. Okay, so
All the three domains of classical mechanics are completely certain. That's the reason why I have, or why classical and quantum are placed separately, because classical is completely certain. Newton's laws of motion are extremely deterministic,
yes,
but
yes,
not quantum.
that correct. So that is what Samin was trying to say with logic. So okay, it's counterintuitive, but it does have logic. Okay, does have some pattern. It does have otherwise quantum mechanics will not work, right? If it has nothing, no pattern, then quantum mechanics cannot predict anything. So it does predict anything. Like Samiran said, it predicts most of the things around us. So that is the reasoning here. And also, one thing that you'll have to be very clear about quantum mechanics is the effects of quantum mechanics are observed at subatomic level. Okay, for example, when Samiran said about the moon, like the moon is not there until you look at it, he was trying to give an analogy. Okay, so right now when you do not look at the moon, doesn't mean the moon is not there. It is still there, but the existence of a particle at the subatomic level. Let's say, for example, an electron. An electron exists in will not exist in any particular location until you look for it. Okay, so the entire physics can be divided into two domains. Okay, subatomic domains and domain of larger objects, like let's say planets or stars. In a way it is like macroscopic and microscopic universe. Okay, microscopic universe deals with particles like electrons, photons, and protons at subatomic level. And there is an entire universe where we talk of planets, and your laptops or your mouse or your pillows. Those are all macroscopic objects. So we have two different theories that are governing them. Okay, the quantum mechanics deals with particles that are at subatomic level. Okay, not definitely at like the moon. Moon is a macroscopic object. When you want to study moon and how it behaves, how it moves around the sun or how it moves around the earth, you use the general theory of relativity of Einstein to study it. At the same time, when you want to study about how an electron behaves or how a proton behaves, you will not use Einstein's theory to study it. You will use quantum mechanics to study it. So we have two theories talking about studying two different aspects of the universe. Okay, now when Samiran says there is a unified theory that is being tried to achieve like a grand unification, it is essentially trying to bring together quantum mechanics and the
Yes, yes.
general theory of relativity. So these two are cannot work together right now. The right now what we have is whatever laws that moon obeys is not obeyed by electron, and whatever laws the electron obeys, the moon does not obey. So we have two different laws describing these two different worlds, macroscopic world and microscopic world. Okay, now the scientists are trying to put their heads together to see if there can be one law that tells us how these both behave. Okay, that is what we are meaning by unified theory. Like these are really complex topics, and my advice to you is, though as tempting as this quantum mechanics is, I would recommend you to pay attention to classical physics or classical mechanics first, and then move on to quantum mechanics, because then it will start making more sense. So it's like moving one step at a time. So right now, classical mechanics is what you will be learning in your schools, in your 6th grade or 7th grade, 11th and 12th. That is what you will learn. Or in for most part of your
In
engineering as well, you
college.
will be, yeah, college also you'll be learning about classical mechanics. So quantum mechanics, if you're interested and if you take up physics as a major, if you want to understand the nature at the most fundamental level, like Samiran said, the fundamental questions, okay, then quantum mechanics becomes a very important aspect for you to understand the nature. So this was the observation that I wanted to make. Okay, a lot of your questions are very valid. I'm not discouraging you. Like for example, Srivatsan asked about strange quarks. It is not our intention not to answer them, but it is beyond the scope of our current level to answer that question. You will have to learn a lot of fundamental other aspects like in classical mechanics and the basics of quantum mechanics before we come to answer questions like strange quarks. And honestly, I'm no expert in quantum mechanics. Even Niels Bohr or Max Planck, the fathers of quantum mechanics, weren't experts. I mean, we can call them experts, but what I'm trying to say is like it is so complex to understand that it would require your basic foundations of physics to be stronger before you attempt to understand quantum mechanics. Okay, and I'm very comfortable with classical mechanics. I can teach you anything that you want to learn in classical mechanics. But as far as quantum mechanics are concerned, me or Samiran, we can talk to an extent, okay, to make you understand. Beyond that, you would need, okay, to understand quantum mechanics, what is that you need? So I can tell you, I can answer that part alone. What is that someone needs to understand quantum mechanics? It is not the logic, it is not the reasoning, it is not anything. It is only mathematics. Okay, you need to understand mathematics. If you are extremely good in mathematics, if your mathematical skills are so strong, like for example, Samiran was talking about calculus, right? If you're very good in calculus and other aspects of mathematics, then you will have a very good chance in understanding quantum mechanics. I mean, that is the closest answer I can give you. What it takes to understand quantum mechanics, mathematics. That's all. Because you're going to talk about probabilities, you're going to talk about chances, and these things are governed by mathematical equations. If you're good at mathematics, you can attempt at quantum mechanics, and definitely you'll get to understand it. That is my final observation. Samiran, I think with this session, what you've essentially done is open up the minds of students who were very curious, and you've been able to handle the questions also really good. I'm happy that this session really went well. Did you guys enjoy the session? Those of you still there,
I
despite your
actually just
hunger,
wanted to, open up the domains of where we are and what physics is all about. So,
and you did it very
yeah,
well, Samiran. I think
thank you.
the objective
That,
was fulfilled.
yeah. So, how was the session as per?
Yes. How was the session? Did you guys like it? Uh,
would they like any more any session on any of these topics on the screen, something like that, whatever.
Yes, everybody is saying they enjoyed it, loved it, very good. I think the responses are largely positive. Thank you, kids, and never stop questioning and keep learning. Yes, we will keep you posted on the upcoming sessions, Nivriti. And if you have any topics that you would like to have a session on, you can let us know so that Harshan doesn't want to stop asking questions. How did they create QM when they don't understand them? No, Harshan, they do understand. So please do not think that people don't understand quantum mechanics. Okay, they do understand. Without understanding, they cannot predict. So there are certain aspects of quantum mechanics that they don't understand. That might be a right thing to say. There are certain aspects of quantum mechanics that is not quite intuitive to human mind, but they do understand quantum mechanics. Otherwise, they wouldn't be able to build the electronics that are used in a mobile phones or a laptops, or for that matter, in any electronics or other aspects in science. They do understand quantum mechanics. So it is not right to say they don't understand quantum mechanics, but there's certain aspects of it which is still not very clear. Okay, that would be the right way to put it. Okay, so thank you everybody for attending the session today. We'll catch you again with another very interesting session in some other topics, and hopefully we'll rope in Samiran again to talk about the theory of relativity, because I'm sure you're interested in that as well. Maybe some other day, not immediately, but some other day. I think Samiran, you can do on it. Okay, there is one request, session on electricity in simple terms. Yes, Nivriti, we can arrange for a session on electricity, sure. So I will end the session. Before I end the session, I would like to hear your voices. You can say thank you and bye. I'll allow you to unmute yourself. Just give me a moment. Let me see if I can allow you to unmute. Yes, I think you can unmute yourself, say thank you and bye, and we can leave.
Thank you, Anna.
Thank you and bye.
Thank you. Thank you. Bye.
Thank you. Bye bye. Yes. See you.